to share this statement. I want to share you with these slides because I found this statement has been used in many events I have attended. Just use include in my presentation for your reference. All right, so in today's talk, I will quickly review how important the pipelines will play in realization of a full-scale hydrogen economy. And then I will introduce briefly the fundamentals of hydrogen-steel interaction and the hydrogen environment. And after that, I will review the research achievement and analyze the gaps existing in hydrogen pipeline technology and based on the fundamental research and the practical applications. Okay, so according to mining, the world is hiding for hydrogen. So if you want, you can find lots of documents and to review the importance of hydrogen in energy transition and the application of hydrogen in different sectors by 2050. At the same time, and different countries and the government bodies has issued the hydrogen strategy documents. So that's 2 examples and published by US and the Canadian government. So in Canada, and the province of British Columbia, Alberta, and Saskatchewan also published the hydrogen roadmap and the hydrogen study and some of the government policies and to realize to want to develop the hydrogen economy in the near future. So the hydrogen economy actually includes 3 interrelated and sections. So you can see from this slide, it includes the hydrogen production and the hydrogen delivery and the hydrogen use. So it's pretty clear and efficient, economic, and safe hydrogen transport. So it's pretty important and to realization of hydrogen economy because it's one of the important component of hydrogen value chains. And currently we have many different methods to transport hydrogen. And it's either transport through the tank trucks or tube trailers and pipelines. So a very quick comparison, and from this table you can see, and when the pipeline is compared with tank trucks and tube trailers, and the pipelines has many advantage in terms of the transportation capacity and the cost and the efficiency, especially for long distance transmission of pipeline of hydrogen. So that's the reason. And the US Department of Energy just issued a statement. You can see transporting hydrogen through existing pipelines and provide a low cost option for delivering large volume of hydrogen. So basically, there are 2 types of the pipelines we usually talk about. One is dedicated pipelines. So that's referred to the pure hydrogen transport pipelines. And the hydrogen is mainly used in the transport and the power sectors. So at the same time, another important topic, and we always talk about, is the blending hydrogen with natural gas. And through the existing natural gas pipelines, it's kind of the blended form of hydrogen transport. So the blended hydrogen is mostly used in manufacturing and the building sectors. We use the existing pipeline for hydrogen service. Actually, there is lots of the benefits. And firstly, it can overcome a high initial capital cost of a new pipeline construction. At the same time, and we have a very extensive the hydrogen pipeline, natural gas pipeline infrastructure. So from the North American pipeline network, so this is a natural gas pipeline network. So you can see the gas pipeline and actually is very extensive, distributed in Canada and in US. At the same time, we have operated and managed the natural gas pipelines over many, many years. We have the experience, we have the expertise, and we have the skilled manpower. So that's make us, and if we overcome certain technical issues, we can use natural gas pipeline to realize and the hydrogen economy as an increased speed. And of course, when we convert the existing pipeline to transport hydrogen, and we do realize there are technical challenges. So these challenges exist in at least the 4 different aspects. And the pipe material, so if the old pipeline or corroded pipeline is safe enough to transport the high pressure hydrogen. And the second is the operation, is related to the hydrogen natural gas blending and some of the operation issues. So number 3 is integrity. For example, the leak detection and how to perform the inline inspection for hydrogen pipelines, and etc. Finally, is safety for the users. And if you have a chance to attend the relevant events, I believe considerable attention has been focused on the transportation of the large volume hydrogen through the network of pipelines. And so that's also consistent with today's topic. And I will focus on the first area of the challenge, that's pipe materials. All right, so that's just a quickly review some background. And the next part is the fundamentals of hydrogen embrittlement. So what is hydrogen embrittlement? And it's a general term and refers to the degradation of metals owing to the hydrogen steel or hydrogen metal interactions. So the degradation, the key word here, actually can mean many different forms of the modes, and I will talk about a little bit later. But firstly, I want to emphasize a very important concept, and hydrogen embrittlement. So what is the hydrogen here? So hydrogen here means the hydrogen atom, H. And the reason is pretty clear. Hydrogen molecules, H2, cannot enter the metal or steel directly. However, the H2 hydrogen molecule can stay inside the metal. So when we talk about the hydrogen embrittlement, we always refer to the hydrogen atoms enter the metals from the environment. So that's why we just emphasize, and it's a hydrogen atom can make the metal brittle. Okay, so when hydrogen embrittlement happens, and I just comment, and it can show the multiple modes of degradation. And the most important degradation of metals is hydrogen-induced cracking. So when hydrogen goes into the steel, and the cracks can be formed and can be initiated by many different mechanisms. I will talk about a little bit later. So this is the most dangerous mode of the hydrogen embrittlement. At the same time, hydrogen can degrade the mechanical property of metals, and such as loss in ductility and reduction in fracture toughness. So they will cause the degradation of mechanical infrastructure integrity and can cause the failure of pipelines. Okay, for hydrogen embrittlement to happen, and usually it includes the 6 steps. So this is the entire process and for hydrogen embrittlement to happen. And firstly, I just comment, hydrogen atom must be generated in the environment. And after hydrogen atom is generated, it will adsorb on the external surface of the metal. So we call it adsorption. And then the next step is adsorbed hydrogen from the outside go into the inside of the metal. From the adsorption becomes the absorption. So we usually call it ADS hydrogen and ABS hydrogen. Okay, after hydrogen atom goes into the metal, and it can diffuse in the crystal lattice of the metals of the steels. And if the hydrogen diffuses randomly in the metal, and usually it can make the hydrogen distribution uniform. So we don't worry too much. However, and there are so many different defects existing in the metals, and it can cause the local trapping of hydrogen. So let's go to the number 5 step, is the trapping of hydrogen atom. If the trapped hydrogen goes to a certain concentration, combined with a certain metallurgical microstructure and the mechanical stress, and then the cracks can be initiated. That's called the hydrogen-induced cracking. So basically, there are 6 steps and included in the entire process. Okay, so first we look at the first step. Hydrogen can be generated in many different environments. So you can see from these slides, it can be produced in heat treatment, electroplating, and welding, and surface treatment, and high pressure hydrogen gas, and we call it a corrosion reaction. So, and anyhow, so no matter what's the source and to produce hydrogen, and please remember, we just talked about the hydrogen atom H. All right, so for pipelines, hydrogen can be produced from outside the pipeline or inside the pipeline. So if we talk about the hydrogen produced from the outside of the pipeline, usually because most of the pipeline are buried structure. So it's mainly talk about from the soil side. And for example, if corrosion happen because of the coating is failed or cathodic protection is not effective. And you can see from these slides, hydrogen atom can be produced by hydrogen evolution reaction. It's an electrochemical reduction of hydrogen ions. And then the hydrogen atom and HADS can either combine into hydrogen molecule H. So if the H2 is produced by either chemical recombination or electrochemical recombination, then we don't worry hydrogen embrittlement because hydrogen molecule and cannot go into the steel. However, there is a certain percentage of the HADS can go into the pipeline steel and become HABS. So this is the mainly mechanism, hydrogen generation and hydrogen permeation from the corrosion reaction. And of course, if the cathodic protection is not properly controlled, and we usually call it a cathodic overprotection, over CT, it can also induce the hydrogen atoms. So that's from the soil side. So if the pipeline carries a high pressure hydrogen gas, and the hydrogen atom can also produce from the gas phase hydrogen. And that's a very simple, H2 directly decomposed into H. So that's from the internal side. And when we talk about the hydrogen pipelines, and of course, our interest in the internal side, that is a hydrogen atom and generated from the hydrogen gas. Okay, there are 2 potential mechanisms and for hydrogen gas H2 to generate into hydrogen atom H. So the 2 mechanisms are either spontaneous dissociation and dissociative adsorption. And the question is, under pipeline operating condition, can hydrogen atoms be generated by the 2 mechanisms, yes or no? And before I go to the further discussion, and just simply look at the graph on my right side. So you can see the H2 decompose into H actually is very, very difficult. And you need to input lots of energy in order for this reaction to happen. So our direct sense is, if H2 and decompose into H, in order for hydrogen goes into steel, actually is not easy because the condition, you need lots of energy and added in the reactions. Okay, so that's a sense and we got from this graph. Okay, anyhow, so if hydrogen and goes into the steel, and I just comment, there are lots of the hydrogen traps can make the hydrogen accumulated and reach a high concentration. For example, and in the steel, there is green boundaries and dislocation and vacancies and inclusions and precipitates and second phase particles. So all of them can serve as effective hydrogen traps. So if the local hydrogen concentration reach a certain threshold value and combined with a stress and a certain steel metallurgy condition, and we just say the cracks can be initiated. Okay, so why hydrogen reach a certain concentration can make the crack initiated? So, and of course, if you have a chance to review the literature, and you can find lots of different mechanisms. But the two main mechanisms, it's a very popular in hydrogen embrittlement mechanism. We call it the first one is a HEDE, hydrogen enhanced and decohesion mechanism. And based on this mechanism, hydrogen atoms can weaken and break the bonding between the Fe and Fe bond. So the second one, we call it the hydrogen enhanced local plasticity mechanism. So according to this mechanism, hydrogen atoms can combine with the internal dislocation and decrease the movement energy requirement for the dislocation movement. So in this way, the hydrogen can increase the mobility of dislocation. And so which mechanism apply for the certain system? And my answer is depends. And we need to think about the mechanical property of the metal and the steels, and what's the steel metallurgy of the steel. And at the same time, also depends on hydrogen atom concentration. So because of limited time, I don't go to much detailed discussion about the mechanism. But basically, and if I use one sentence to quickly summarize the fundamentals of hydrogen embrittlement, so you can say for hydrogen embrittlement to happen, it depends on three interrelated conditions. So we need to think about the steel metallurgy, we need to think about the mechanical stress, and finally, the local hydrogen atom concentration. All right, and when we talk about the hydrogen embrittlement of pipelines, so and then let's go to the current research progress and some of the gaps and analysis of gaps. Okay, the first thing, and how hydrogen atom generated in high pressure hydrogen gas environment. I just introduced in the fundamental section, there are two mechanisms. The first one is a spontaneous dissociation of hydrogen molecules. So this reaction is simple. And you can see on my left side, on the top left side, based on this mechanism, H2 hydrogen gas decompose into H, that's a hydrogen atom. So when we calculate the free energy change of this reaction, and according to the different hydrogen pipeline operating conditions, such as temperature and pressure. So you can see, and all the conditions, the free energy change of this reaction are positive. So we have known if the free energy change is positive, so that means this reaction is thermodynamically not possible. So based on the thermodynamic analysis, and we can have an important conclusion, and the pipeline operating condition, the spontaneous and the dissociation of hydrogen molecule is not possible. So that's why we don't need to worry the hydrogen atom generation by this mechanism. And because the thermodynamic calculation tell us the answer is low. Okay, how about another mechanism? That's a dissociative adsorption. So, and on the left top side, you can see this mechanism, and we also can write the reaction. Hydrogen gas, H2, adsorbed on the surface of the steel, and we use crystal phase 100 as an example, and this reaction can generate the hydrogen atom H. As the same thing, we also perform the thermodynamic calculation. So you can see the results here, and the different temperature and the operating pressure, the free energy change actually are all elective. So this calculation tells us, and when we use the pipeline to transport the hydrogen gas, and the hydrogen atom, yes, can potentially generate it based on this mechanism, because the thermodynamic calculation tells us yes. So that's why, and potentially the hydrogen atom can be generated and goes into pipeline steel to cause a hydrogen embrittlement if we use a pipeline to transport hydrogen. Okay, and the same thing, I give the main results and the thermodynamic model here, and just share with you. And we need to care about this problem. Okay, and that's the first important thing involved in the hydrogen atom generation. The second, when we use the existing natural gas pipeline to transport hydrogen, and the very quick question, how the method, the CH4, and that's the main component of natural gas, will interact with the hydrogen as a H2. Consequently, will influence the absorption and the dissociation reaction. So that is related to the influence of the two major and gas component, and when we use a pipeline to transport the blended form. Okay, and in order to have this answer, and the same thing, we also build a certain model and to determine the thermodynamic possibility of the methane molecule, CH4 molecule, and absorption on the steel surface. So the thermodynamic model also tells us, and you can see from these results, and the different temperature and the CH4 pressure, the green energy change, the delta G, are also lective. So that means thermodynamically, the CH4 molecule can also and absorbed on the steel surface. So if the CH4 and the H2, they co-absorbed on the steel surface, there is a competition and of the two gas molecules. So that's why, and if the H4, that's the methane partial pressure going up, it can decrease the possibility of hydrogen embrittlement. Because what? Because the two gas molecules will compete each other in terms of the absorption on the steel surface. So from the hydrogen embrittlement perspective, and when we increase the partial pressure of the methane molecule, and the hydrogen embrittlement possibility will be going down. So this is a direct answer and from the thermodynamic analysis. Okay, the number 3 important question and related to the permeation of hydrogen atom from the outside steel go into the inside of the steel. So I just quickly share with you the methodological analysis results, and I don't want to touch too much the steel metallurgy because I think the audience has a varied and background. But basically, when hydrogen atom goes into the steel, and if the hydrogen atom can distribute it uniformly everywhere in the crystal structure of the steel, we don't worry hydrogen embrittlement, because the uniform distribution can make the local concentration of hydrogen maintained at a low level. So that also means the certain steel has a certain tolerance to the hydrogen atom. Okay, not a single hydrogen atom can cause a cracking problem. No, there is a certain tolerance to hydrogen atom accumulation. And so uniform distribution of hydrogen is not a big trouble to the steel. And we introduce in the fundamental part, and what we worry is the local trapping of hydrogen. So that's a local accumulation of hydrogen atom to reach a certain concentration. So how to visualize and how to measure the hydrogen atom is local accumulated. And I will say it's not easy because the hydrogen is pretty small, and the direct observation actually is a very challenging task. And fortunately, the modern surface analysis technique and enable us to go to the very small resolution. And for example, in the University of Calgary, in my lab, and I have equipped the advanced technique. And you can see, I just share with you the major results. So if there is a micro dent in the steel, and the hydrogen atom actually can accumulate it as a dent area because of stress concentration. Based on the, you can see the different color on the left side of these slides, and we just seen the hydrogen atom is accumulated here. The same thing, we can also use a technique to observe the different tendency of hydrogen atom accumulation in the different metallurgical phase, such as pipeline steel mainly includes ferrite and pearlite. So the different metallurgical phase has a different tendency to trap hydrogen, and based on the different color from the middle graph in the slides. So anyhow, so this slide just tells us if we want to visualize the hydrogen distribution in the steel, and we need to have some equipped certain surface analysis technique, and this will give us the direct answer. If hydrogen goes into the steel, where it will stay. Okay, when we use the steel pipeline to carry the gas, such as a natural gas, our knowledge has told us the natural gas usually experience pressure fluctuation. So it will influence the stress corrosion cracking very much. So that's why some people just regard the hydrogen stress corrosion cracking, pipeline stress corrosion cracking is a special form of corrosion fatigue, because pressure fluctuation induce a certain cyclical stress to cause cracking and propagation. The same thing, we will use the steel pipeline to carry the hydrogen or blended hydrogen with the natural gas. And the very concern and the big concern is how hydrogen will influence the fatigue cracking. So that's the interaction of hydrogen and fatigue. And for example, and compare with the static stress. So you can see from these results, and the hydrogen, the plastic stress actually can facilitate hydrogen atom accumulation, but not the permeation. But if the stress is cyclical, such as pressure fluctuation, the change in frequency actually tend to accumulate hydrogen atoms in the steel. So that's and at the same time, if the hydrogen goes in the steel, usually it can speed up the fatigue crack growth. So that's why under the hydrogen and the fatigue, actually they can make the pipeline failure and quickly, because hydrogen can speed up the fatigue cracking process. Okay, when we talk about the hydrogen embrittlement or hydrogen-induced cracking, and we realize the pipeline is a welded infrastructure. So the welding area are always sensitive to hydrogen-induced cracking because it has a unique and metallurgical microstructure, and it also has a local stress concentration, just as a simulated results here. Consequently, the hydrogen atom tend to accumulate in the welding area, such as a heat-affected zone. So the special steel metallurgy and the local accumulation of hydrogen and usually can make the crack and preferentially start in the welding area. So that's why and develop the numerical model and to simulate the trapping of the hydrogen as a welding area is a very interesting research topic. And the industry is also interested to learn the knowledge from this topic. And in terms of the hydrogen prevention, from the metallurgical design, I will speed up a little bit. And there is a many proposal and to modify the pipeline steel metallurgical process, and but a very common method and to process the non-mechanical inclusion, because the current research found if the inclusion becomes a sub-micron scale and uniformly distributed in the steel, it can decrease the local trapping of hydrogen atom. Consequently, it can make the concentration of hydrogen and inside the steel goes to a very low level. So that's why the hydrogen embrittlement and can be reduced. And when we use the aged pipeline to transport the hydrogen, actually we also have additional challenge we have to overcome before we just convert the pipeline in hydrogen service. So the first thing we have to realize, after a long-term of service, the natural gas pipeline usually contains such as dents, corrosion defects, and the micro cracks. So these defects and tend to be an effective hydrogen trap, and because it's a stress concentration. So that's why we have to develop a technical assessment program to evaluate how effective these defects will trap hydrogen atom. For example, if the pipeline contains a mechanical dents and our simulation just directly tell us, and based on simulation results, hydrogen atom will tend to accumulate as a dents to make the local hydrogen concentration and reach a high level. So the same results also apply for corrosion defects. And you can also see from these simulation results, no matter the corrosion is an internal defect or external defect, and the hydrogen atom also tend to accumulate as a corrosion area. So that's also makes the local hydrogen and reach a certain concentration value. And consequently, the hydrogen-induced cracking tend to happen as a corrosion defects. So if the pipeline still contains, I will speed up and quickly wrap up. If the aged pipeline contains the macro cracks and the simulation results also shows the macro cracks because of the local stress concentration can also trap the hydrogen to make the local concentration reach a certain value. And so that's the aged pipeline has a surface defects. At the same time, and the aged pipeline usually experience a pipe-soil interaction, especially in some geotechnically unstable regions, such as a mountain area. So the research results has found if the soil and induce a certain strain on the pipeline steel, the pre-strained steel is sensitive to hydrogen local trapping and consequently to cause the hydrogen-induced cracking. So that's why to simulate the hydrogen pipe-soil interaction to evaluate the soil strain and influence the hydrogen accumulation is a very important and technical evaluation program. Okay, so finally, and in addition to CH4 molecule, the carried gas probably also includes the oxygen, the water vapor, and some other gas components. So how to assess the influence of this impurity gas on hydrogen generation, and is also an important technical evaluation topic. All right, to conclude my talk, I think it's time. And I just say the hydrogen pipeline is currently a very hot topic, no matter in European countries, in Asian countries, and in North America. And the hydrogen pipeline and attract the wide attention. And but basically, I want to conclude the three important remarks. And before we convert the existing gas pipeline for hydrogen transport, we need to develop a detailed technical assessment program. And in order for the pipeline to transport the hydrogen safely and efficiently. At the same time, we have to develop the standards to get the industry and for the conversion. Finally, we have to realize there is extensive scientific and technical gaps to be filled in this important topic. All right, again, I thank you very much for your attention, and I will be happy to take any questions. Thank you.
Thank you very much for that presentation, Professor Cheng. Can you hear me?
Yes, I can.
Okay, perfect. We'll open up questions to audience in person. Does anyone have any questions? Okay, we have one.
Thank you for the presentation. A deep insight into my question is, you talked about a few sequence of process that lead to hydrogen. So my question is, if we take away one of that process, does that stop hydrogen from
I'm sorry, I cannot hear you clearly. The reason is the voice is not enough. At the same time, it seems the microphone will cut your voice. So that's why I cannot listen to a sentence. I just listen to the certain words.
Okay, not to worry, I'll repeat the question for you. So the question was, you've identified a sequence that would lead to embrittlement. If any parts of that sequence were removed, would the failure mechanism then disappear?
The same thing. The same thing. I cannot listen to sentence, and it's just the words, and words, not the sentence. So it seems you asked me some question related to the processing and the influence of some the processing parameter of something like that, right?
Okay, can you hear me now? Is it clear?
Yeah, I can hear you. Yes.
Okay, perfect. So the question we got was, you listed a sequence that would lead to failure with hydrogen embrittlement.
Oh yeah, okay.
If any part of that sequence is removed, does that then remove the failure mechanism?
Any sequence of what? Sorry.
So if any part of that sequence is then removed from the process, does the
Okay, all right. So any sequence move to the process. Okay, all right. So firstly, yes, thank you for your patience. And firstly, I just say for hydrogen embrittlement to happen, and you can see there are 6 steps included in the entire process. And for hydrogen pipeline to operate, and if we want to, for example, reduce the hydrogen embrittlement sensitivity or even stop the problem, and we can control the hydrogen generation from the first step, for example. And if you reduce the operating pressure, or you control the carried gas and the composition, and you do reduce the hydrogen atom generation. And for example, you can increase the partial pressure of the natural gas and reduce the partial pressure of the hydrogen. And consequently, our calculation results tell us the hydrogen generation sensitivity can going down. So that's a typical example. We just prevent this problem from the step 1. And in terms of other steps, of course, you can improve the steel metallurgy processing technique and to increase the resistance of steel to hydrogen embrittlement. And yes, the answer is yes, you can control the problem from the certain steps in the entire process.
Perfect, thank you very much. We've got one more question. So
yes, thank you very much, Professor Frank. Interesting presentation. My quick question is that is there any methane to hydrogen percentage ratio, or is there any pressure that can be critical factor? Therefore, we can actually use our old dirty steels where we don't know where the micro cracks are already existing, and we have not probably picked them up through our inspection regimes.
Okay, so let me repeat your question. And it seems to me your question related to the hydrogen trapping in the local, for example, micro cracks on the aged pipelines. Is correct?
Yes.
yes,
Okay, all right. So the technical assessment of hydrogen trapping as these local defects and the macro cracks actually depends on the inline inspection first. So the industry, the pipeline operator, and performs the inline inspection to gather information in terms of the defects and the macro cracks. So, and we got the location and the dimension and the geometry. And then the next step, based on the ILI gathered information, we develop the numerical model and to simulate how the different size or dimension or geometry of these defects, and will generate a certain stress or strain concentration. And the number 3 step, and how this stress concentration will trap and make the hydrogen atom and goes into this area. So basically, assessment has 3 steps. We got the ILI data, we got the stress concentration in this area, we got the hydrogen atom diffusion and the local accumulation. So that's we have what we have developed and in my lab, and we use the filament element model and to perform this technical assessment.
excellent. Thank you very much. Okay, I think we've got time for one online question. So we'll go with the one in the middle. So it's by
Oh, okay.
Mickey. And it says, if hydrogen is transported purely by drying, would the hydrogen enrichment still occur?
It's purely dry. Okay. It doesn't matter is dry or white. And you can see if the carried gas is white, we need to think about the influence of the water vapor. So water vapor is very interesting. Sometimes it can make the situation worse to increase the hydrogen burden sensitivity, but sometimes it can decrease the sensitivity. But even the carried gas is super dry, 100% dry, but the hydrogen atom can still generated by decomposition of hydrogen gas. So that's why the answer is yes. Even the carried gas is purely dry, hydrogen burden still can happen if the H2 can decompose into H under the conditions.
Perfect. Thank you very much. And we just got one more question. So please take the name.
Hello, my name is William Ritchie. As far as I can tell, there seems to be some real leaps forwards in our understanding of for transportation systems. I was wondering where you think the international standards and design codes are at the moment in terms of keeping up to date with these developments, if they're suitable, or whether you see any significant upcoming things.
Okay, so let me repeat your question. I still hear the couple keywords, and you asked me. Currently, we have some standards and to regulate the hydrogen transport by pipelines. So, but why we still concerned some of the issues related to the problem or related to the standard, right? So it's a question, right?
Yeah.
Yes, that's
Oh,
right.
okay.
That's suitable for service.
I'm sorry.
Yes, he's asking whether they're suitable for service.
Okay, all right. Okay, so if my understanding is correct, and we do have some of the standards available to regulate the hydrogen transport by pipelines. For example, in North America, I think in European countries it's the same thing. We usually refer to the SME and the standards and for this purpose. But we have to realize these standards usually apply for the low pressure hydrogen transport. At the same time, and you can see from my current slide or today's slides, hydrogen burden actually depends on 3 interrelated factors. That's a steel metallurgy, mechanical stress, and hydrogen. So, and the current standards and in my understanding do not include the 3 factors into consideration at the same time. So that's why when we convert the aged pipeline for hydrogen service, actually the technical assessment supposed to be case by case, and we cannot depend very much and on the standards. We need to collect the information of specific pipelines and then perform the technical assessment. So that will give us the comfortable results and to make the conversion and feasible. And so that's the first thing. That's a case by case and assessment. The second thing, and the standards usually apply, I think applies more comfortable for the new pipeline construction, but it has a limited application for the old pipelines, such as the existing natural gas pipelines. So that's a certain limitation. So that's why, and the key point of my talk, and you can say is focus on the conversion of the existing pipelines. So that's why we cannot depend on standards. We need to develop the technical assessment, perform the case-by-case assessment.
Excellent. Thank you very much for your answer today. So unfortunately, that's all the questions we have time for. But if anyone has any additional questions or queries, please feel free to contact Aberdeen branch or contact Professor Cheng directly, and we'll look to answer them in the follow-up Q&A session. So if you can, we'd like to thank Professor Cheng in the usual way. Thank you very much.
Yeah, thank you very much.
Okay, thank you very much. So for our next presentation, well, previously we've been talking about hydrogen. So for our next presentation, we're going to be talking about CO2. And for that, we have Dr. Shravan Kairy, who's going to be joining us today. So, and they'll be giving us a presentation on the challenges in assessing corrosion resistance of pipeline steels against CO2 emitters. And just to give you a brief introduction before we start. So, Dr. Kairy is a high research scientist at MPL UK. His research focuses on understanding corrosion of pipeline steels in dense CO2 phases and developing a standard test methodology going forward. He has published 29 peer-reviewed papers and has received career research awards at the 17th ICAA in 2022 and previously won the NACE A.B. Campbell Award, the Vice Chancellor's Commendation, and NACE Marcel Fourier Prize. His 15-year work experience spans Sandvik, Asia, CSIR National Metallurgy Laboratory, and Monash University. Shravan did his PhD in Material Science and Engineering at Monash University in Australia in 2017. He completed his MTech in Materials and Metallurgy at IIT Kanpur in India in 2010 and BTech in Metallurgy and Material Technology in JNTU Hyderabad, India in 2007. I'd like you to invite him up to present in person. Thank you very much.
Thanks, Philip. Yeah, thanks, Oli, and thanks, Shravan. So, welcome, guys. Today, I'm going to talk on the challenges in assessing the corrosion resistance of pipeline steels against CO2. So, here is the outline of my talk. So, what I do is I just introduce the carbon capture and storage, and how the CO2 is transported by pipelines. What are the conditions? And what's the current status and the challenges we have in corrosion measurements. And before going into the test methodology, I'll introduce what are the factors that influence the corrosion of pipeline steels and different setups that are used for assessing pipeline steels, and what is the common methodology that is normally employed, and there are any issues in the methodologies and any potential solutions. And I'll be commenting on the reliability of corrosion measurements, and finally summarize the topic and provide some recommendations. So yeah, without much delay, so let's enter into the CCS world. Corrosion. So the carbon capture and the storage is a process of capturing CO2 from industries and transported through pipelines or ships, and it can be and stored underground. So based on this, the CCS has a significant potential to decarbonize fossil fuel power plants and various industrial sectors while limiting CO2 emissions into the atmosphere. And as we have learned from Bell's lecture, that for providing generating 1 ton of steel, so approximately like 1.8 tons of CO2 is released, and which is equivalent to 8% of the global CO2 emissions. So if we can capture the CO2, is really awesome. So the CCS is a key technology to achieve net zero targets and combat climate change. So how the CO2 is transported? It can be transported via pipeline ships and the roadways, but the pipeline transport of CO2 is more economical and safer. And here is the phase diagram which shows the different phases of CO2. So, and it reveals the pipeline transport for CO2 is carried in the dense phase. So the dense phase is normally considered over this critical temperature, which is the liquid and the supercritical phase. So in the open literature, it's not very clear what exactly the pressure and temperatures at which CO2 is transported. But one indication is that it has to be in the liquid or supercritical phase, which is over this critical pressure, so avoiding the gas phase. And this is because of the high throughput transport of CO2. And the higher pressure requirements is based on the material specifications and the cost. And the temperatures normally depends on the ambient conditions. So here is the global CCS status. So on the left side, you can see the different CO2 emitting industries. And these are the red circles of the CCS facilities that are currently in operation. And so the considering the importance of the CCS technology, so in the coming decade, there are several CCS facilities are currently in the planned and advanced development stage, and also extending to several industries. And these are the proposed that are in the United Kingdom and Ireland. So if you want more information, you can go to this Global CCS Institute. So based on the experience, so it has been in practice since 1971 and primarily in the USA. So the low carbon steels API grade are used as they're economical and reliable, and most of the pipelines are for enhanced oil recovery. So again, we have very little information, and based on this, there are 39 pipeline accidents occurred from 1986 to 2008, and the corrosion accounts for 45%. So let's see like why the corrosion occurs in the CO2 pipelines. So CO2 contains several impurities such as water, oxygen, and there could be many, and depending on from where CO2 is captured. So normally CO2 is non-corrosive, but and as long as even the water is in the dissolved state. But what happens is that once the water condenses, so the CO2 is dissolved in the liquid water, and also the other gases also dissolve. So for example, here is a case of formation of carbonic acid and the nitric acid. So the corrosion occurs by dissolution of iron supported by cathodic hydrogen reaction. So what could be the reason for water to condense? So one thing is the variation in the temperature and the pressure. So the solubility of H2O can decrease, and also have the impurity content. If the impurities are more, the solubility of H2O in the CO2 decreases. So for example, if you have a more pipeline networks coming from the different streams, and though H2O is in the soluble state, but coming CO2 from the another network, from the other pipeline network can decrease the solubility of H2O, and this can cause water condensation, subsequently corrosion. So currently, do we have any standard specifications that this could be the impurity content? The answer is no. So there is no lack of accepted standards specifying impurity limit CO2. So the majority and a few of the recommendations are majorly based on health and safety. In the case that if there is any accident and the release of these toxic gases into the atmosphere. And also there are some of the recommendations for H2O, but corrosion can still occur at this water content. So one thing is managing strict concentration limits via purification process also increases the cost of CCS projects. So it is very important, like whether we can provide the confidence on the accuracy of the measured corrosion rates. So based on that, whether we need to do a corrosion management or whether we need to go for a strict purification process, we can make a decision based on that. But before that, we need to have a confidence on the corrosion rate measurements. So what are the challenges we have? So the safe, reliable, and economic transport of CO2, that's the one thing. So currently we have a limited global experience in transporting anthropogenic CO2, as we are seeing. We are going to capture more CO2 from different sectors. And the failure of pipeline corrosion can lead to fatalities or injuries. So actually the thing with the CO2 is it's non-toxic and non-flammable, but the issue is it's denser than the air and it can settle in the low regions, and it's also it doesn't have any smell or and we can't see that. So what happens is that we have a little warning before the people can breathe CO2. So it's very dangerous. And second thing is the standard test methodology tests the corrosion of pipeline states in dense phase CO2 does not exist. So this is our major focus here. So this, for the successful deployment of the CCS technology, we need to have confidence on the methodology of assessing the corrosion of pipeline states in dense phase CO2. So before going further, just I'll introduce like how the corrosion rates are measured. So one is time average corrosion rates. So specimens are exposed to the dense phase CO2 and measure the mass loss. And second thing is measuring of localized corrosion rates. And what will be the typical values that we are talking here? So a pipeline steel of X65 grade, just containing the water, it doesn't have any impurities. So the measurement value is less than typically 0.4 mm per year, and the localized corrosion rates are higher than 1 order of magnitude. So these are not really acceptable. And having more impurities, the values are significantly higher. So before going into it, we need to know what are the factors really influencing the pipeline corrosion. So one is dense phase CO2. So the impurities, what are the impurities that has in CO2, and the pressure and temperature and the flow rates. So, and from the pipeline is the grade of the material. So the well sections and internal surface roughness and the stress. So these I'll be discussing in the coming slides. So one is the concentration of impurities is very key. So during the whole duration of the testing is key, because what happens is in the CO2 stream, there are continuous replenishment of the impurities, because there's a continuous flow. But normally the testing, there could be a depletion of the impurities. So we need to have a control of the concentrations. And how it can be done is by periodic or continuous analysis of the impurity concentration during the testing. So one thing can be is by gas analysis. So measurements, but the issue with that is only possible at atmospheric pressure. So what happens is once we, so here you can see the change in the solubility, water solubility in the CO2 as with variation in the pressure. So from the gas CO2 to going into the liquid phase, solubility of CO2 varies. So if you have to measure the concentration of impurities, so significantly is different. So there could be an issue with the errors coming up with the analysis. And there's one more like FES spectroscopy, which is can be measurable at the test pressure, but there are more complications if there are more impurities. So it's right now it is completely not well established of measuring the impurities during testing. So, and another factor is during the testing, we need to have a close control of temperature and the pressure. So if you can see the corrosion testing is happening at 25 degrees centigrade, and the temperature suddenly falls during the testing to 15 degrees centigrade. So there is a decrease in the solubility of the water. So which is it is like 500 ppm. So if you are very close to the solubility limit, and a fluctuation during the testing can have accidental condensation of the water where the corrosion can take place. And second thing is the pressure. So normally with the decreasing in the temperature, the CO2 solubility increases in water, and also similar to the gaseous impurities. So what this tells is that the higher is the solubility of the CO2 or the gaseous impurities in water, the corrosivity of the condensed water increases. So, and how the temperature and pressure can also play a role on the corrosion rates. So one is the durability of corrosion products. So normally with the increasing in temperature, the corrosion products are more compact. So again, it depends on what the corrosion products that are forming. And the influence of pressure on the productive ability is currently unknown. So one thing, so what we need to do is considering the importance of temperature and pressure. So we need to have a continuous monitoring and control of temperature and pressure are required, and also the independent control of temperature of test specimens. So this is also has not been established. This is important because the pipeline surface have a temperature influence from the surrounding atmosphere, and there could be a temperature change close to the surface and can have an influence. So, so independent control of temperature is very much essential, but none of the experimental designs have managed to design that kind of experimental setup. So the third one is the flow rate. So let's see, like, what are the options that can what could be the influence of flow rate on corrosion. So there are three possible things that we can think of. One is wall shear stress. So what happens is, yeah, sorry for the resolution here. So So the wall shear stress, what happens is, so when there is a flow on when there's a flow of CO2, it can generate a shear stress. So, and the corrosion products can be disrupted, and there is a region where the corrosive solution can go to the surface beneath and cause the corrosion of the pipeline steels. So so the typical, again, the flow rates are in the industry is not very clearly revealed. So typical what we could find is typically lower than 2.5 meters per second of CO2. So what it was found is like the wall shear stress generated is just like 1 Pascal, and the adhesion strength of FeCO3, which is developed in different conditions, is significantly higher. So which means this wall shear stress cannot disrupt the corrosion products. So in contrast to that, different studies have indicated the disruption and spallation of corrosion products. So which means the wall shear stress generated could be sufficient to cause disruption and spallation, and also depends on corrosion products. And can increase the corrosion rate. And other one is the solid particle impingement. So right now we don't know if there is entrate sand particles within the CO2, but if there is spallation corrosion of corrosion products, so this can contribute to this one. And there is also a study which indicates the liquid droplets can also influence, but there's no validation and there's no clear understanding out of it. And currently there are no test setups and studies which indicates there is an effects on these solid and liquid droplets. So these are the negative impacts. So what could be the positive impact? So there is a hypothesis mentioning the displacement of condensed water droplets with flow and decrease the corrosion rate. So, so if you have the water droplets in the CO2 pipeline, so this flow will displace the water droplets, so it doesn't lead to settle on steel pipeline, and corrosion can never be occurred. So, so these guys have done the modeling calculations. So, what is the critical size for the droplet to be displaced? So, what they have found that is there is a critical size for it. So, the corrosion can still occur if the particles are below the critical size. And the majority of the studies, so what it has been observed is that flow rate increased the corrosion rate by significantly 1 order of magnitude, and different groups have indicated there is negligible difference, and other groups have indicated there is no difference. So right now, the current status is there's no consensus on the influence of flow rate and corrosion rates. So what they have done to generate the corrosion rates is the one way. So this is the autoclave, schematic autoclave. So the specimens are static and the impeller is used to generate the flow. In other case, the people have connected to a rotating shaft to generate the flow. So here you can see the CFD calculations simulating the flow velocity within the autoclave. So here you can clearly see, so these are the velocity of flow rates. So you can see that it is non-uniform within the autoclave. So one specimen having a different location within the autoclave can experience different flow velocities. So majority of the studies, what they have done is they have compared the corrosion, compared different studies based on the rotation rates. So this should not be done because samples within the same autoclave system can have a different flow conditions. So it can vary with the rotation rates and design of the impeller, so the volume and design of the autoclave and test specimens, the shape, position, motion. So this could be so many things. So the comparison of the studies just based on the rotation rates of the impeller cannot be made. So what we need to know is understanding the linear flow rates, and the wall shear stress also need to be determined. So Dust et al. Have group also generated the flow by using this, the slim autoclave systems where the test specimens are loaded to the specimen holder, and these autoclaves are continuously rocked or rotated. So, and you can generate a better fluid flow around the specimen. But they have limitations on the specimen size because the weight determines the velocity, And also the mechanical impact could potentially disrupt corrosion products. And also you can't use this for testing stress corrosion cracking tests where the specimen is loaded to a stress corrosion cracking jig. And also the flow direction alters periodically. So another ideal systems are the flow loops. So this can be representative of surface depending on the test design. So if you have the pipeline kind of loop and having the specimen in the pipeline shape, so you can generate the flow conditions similar to that. So there are different type of flow loops that are there in the literature, but actually they can be more unique autoclave flow loops that can be designed. But right now it is very complex to generate the service conditions, such as having the flow generation over the well profiles or U-bends or vertical or horizontal. So right now it is premature to judge whether exact service conditions are required. Considering there are several uncertainties of controlling the composition itself. So the other factors, factors that influence the corrosion rate is from the pipeline material. So the pipeline grades such as different API grade steels or corrosion resistant steels. So what the studies reveal is there's no significant difference between different API grade steels like 65 or 75 or 85. And even the corrosion resistant alloys, such as stainless steels, experience similar corrosion to API grade steels. And the key is controlling the impurity concentration. So even when the impurity concentration is significant, forming a very high acidic corrosive medium, so even the highly corrosion resistant has to experience corrosion. So the key is control the concentration of impurities. And the well section have the microstructure heterogeneity and residual stress and defects. So we have seen from the previous Frank's talk, so there could be a significant difference and can cause corrosion and also contribute to stress corrosion cracking, but not many studies exist in this. And surface toughness of the pipeline, this is the internal surface, can increase the wettability and also act stress raisers. So, and another factor is the stress corrosion cracking. So EIC occur in gaseous CO2 containing H2O. So normally, how it is tested is using the 4-point bend specimen. So everything is exposed and see if there's any cracks on the surface, and there's a different setup here. But there are only like 5 or 6 studies in this studying the EIC intensified CO2. None of the studies reveal that these steels suffer environmental induced corrosion. So right now, so we have seen what are the factors that contribute to corrosion. So now let us see what is a commonly practiced methodology, whether all the factors are taken into account. So here is a procedure. So this is an autoclave. Normally normally used for studying these pipeline steels. So water is added in the liquid state. So then the mounting of the specimens and sealing the autoclave and adding the impurities of gaseous impurities and pressurizing the autoclave to the desired test pressure and temperature, and the test procedure initiated once it is stabilized. So normally it takes like 1 to 2 hours. And after the test procedure, depressurize the autoclave and clean the specimens and measure the mass loss. So this is a majority of the studies, almost 90% have followed this methodology in the past decade. So significantly, there are several issues. One thing is the control of the concentration of impurities, which is lacking because the concentration of impurities are not measured during the testing. So it is measured prior to putting into the autoclave. And the degradation of the autoclave and the Moreland et al. Have identified the other issues like accidental splashing of water on specimens and condensation of water during depressurization and actual test duration. So all these factors contribute to the errors in corrosion rate measurements, which I'll be going through. So one is H2O content. So So the amount of the water which is added into the autoclave is lost during the deaeration with time. And this will not be an issue if you have more water that is added in the autoclave. But if the water is having close to the solubility limit, so the loss of water during the testing, I mean, prior to the testing or during the initial process can have a lower than the solubility limit. And other one is the concentration of gases impurities. So we all know that the gases that dissolve in the condensed water. So before that, so these can also dissolve in the liquid water. So whatever the gases, concentrations of impurities that are put in the autoclave are normally lower than the intended values. So technically, the test specimens are not exposed to the intended test environment for the entire duration of the test. And so what is the key is we need to have a continuous monitoring system. If there is a depletion, then either stop the test or replenish the test environment with the impurities. So other one is the quality of the deaeration process. So the CO2 is abundant in the atmosphere. So deaeration is the key. So oxygen, what happens is it forms less protective film Fe2O3 than FeCO3, and also and it can increase the corrosion rates. So the coal, what et al. They have calculated is that so if there is 1,000 ppm of oxygen in the dense phase CO2, very little goes into the condensed water phase. So which is if it is 1,000 ppm photo, it is less than 10 ppb. So oxygen should not really play a key role, but several studies have indicated that oxygen takes an electrochemical reactions and also significantly increase the corrosion rate. So one thing is we need to check on the quality of the deaeration process or understanding more if there is any real effect at this concentration limits. So the possibility of the water splashing on the test specimens was revealed by in situ visualization during the testing. So Moreland et al. have custom built an autoclave having a visual window during the testing. So this is the initial droplet. And while pressurizing the autoclave, you can see a splashing of water over the whole autoclave. So you can see the water splashing on the test specimens. So corrosion initiates at the starting of the test itself from the splash water rather than from the condensed water. In this case, the corrosion can be higher. So most of the corrosion studies have been taken in the closed system where the occurrence of splashing is unknown. So how it can be avoided is one, by adding water in the dissolved state or by introducing physical barriers such as this one. But we need to take care if there's any flow, want to introduce any flow of the specimens. So this is the condensation of the water. So normally what we do is at the end of the testing, so we depressurize the autoclave. So, So the depressurization of the autoclave. So we have seen the influence of the temperature and the pressure on solubility of the water. So once you start to depressurize, the solubility of the water decreases, and that leads to condensation. These guys have observed that the corrosion rate is like 0.03 mm per year, although it did not suffer any corrosion during the exposure. So what happens is if you take more time, more time to over the autoclave and cleaning, so the contribution of corrosion, contribution from the condensation of the water during depressurization will be more. So how we can avoid is by purging the autoclave with CO2 prior to depressurization. So another is the test duration. So what is the test duration mean? It's a time during which test specimens are exposed to the intended test environment. So, but what is the commonly considered is the one where temperature and pressure of dense phase CO2 are stabilized. So normally what happens is once we add the liquid water, so to go into the soluble state, it takes like 7 to 24 hours. So it also depends on different experimental conditions. So technically, the test specimens are not often exposed to the intended test environment for the whole duration of the testing. So just to clearly give a view, so this is a general corrosion rate measurements, corrosion rate measurement. So it has a contribution from the mass loss and the area of test specimens and the time of test duration. So from the previous understanding, we have the mass loss from water splashing and accidental condensation of water on the surface during the depressurization. And also the time is not accurate, it's more than what the actual time and the area of this corrosion. So you can see that the area of corrosion is significantly lower, and in some cases it's significantly higher, but normally the whole area of the test specimens are taken into the consideration. So the reliability of the reported corrosion rates is questionable. So what we have done is we have compared the corrosion rates containing only water as an impurity, because several studies have used different concentration of impurities. So it is very complex to compare one study from the other study, and considering that several factors influencing corrosion. So even having just a water as an impurity is also very complex, having different exposure conditions, the flow rates. So one thing we can see here is H2O is undersaturated, so which means H2O is in the soluble state, but the corrosion rates are significantly higher, and in some cases almost equal to the saturated limits. So once the H2O is in the soluble state, it should not condense to cause any corrosion. But we have seen there's a reporting of corrosion even in undersaturated conditions. So this could be due to improper control of test parameters during testing. And in the H2O as well, so it's very complex to compare because of different varying parameters, but there is one conditions where everything is the same, like 50 degrees centigrade pressures, flow rates, and the time, but there's a significant difference of 1 order of magnitude difference from one study to other study. So based on this, so this is the data from the last decade. So it is very highly concerning. So it is very serious issues and reproducibility. So it is very hard to compare from one laboratory test to other laboratory tests, and we can't deduce any reasonable conclusions based on the flow rates, based on the temperatures, or based on pressure. So it's really concerning. And similarly, localized corrosion rates as well, and that typically 1 order of magnitude that has been reported. And second thing is normally the word people use pitting for these cases for the low carbon states. So it should not be confused with the pitting in corrosion resistant alloys. So what here exactly means is they have this localized corrosion, and which are much deeper attack compared to the other regions. So it's better to call it a localized corrosion regions. So it's yeah. So it's also what discussing about the electrochemical measurements. So electrochemical measurements normally can give understand of the corrosion mechanisms and also determine instantaneous corrosion rates. But the thing is, it has also like that reliability and to a greater extent than the mass loss. So the issue is that the condensed phase is very low in volume, so it can't normally wet conventional size electrodes. So what people have done is to miniature these electrodes so that the condensation on these electrodes can provide electrochemical understanding. But still here, we can't polarize the electrodes to very high potentials because of having a low volume. So this is a summary and recommendation. So literature, what we have in the past decades, intense-phase CO2 is characterized by lack of reliability and due to challenges in control of test parameters. So there's a clear need for the development of a standard methodology and to generate industry relevant data. So NPL is embarking on a research program to develop such a standard method, and please contact us if you're interested. So here are the acknowledgements. So goes to Dr. Gath Hines, Dr. Ellen Turnbull, and Dr. Shingizo. and funded by BES and also Preserve for hosting the event. So here are the opportunities to work. So normally the one is the A4I, so industries can apply for that. And there are several rounds during the year and the commercial projects, and you can join the industry advisory group meetings. So it normally occurs twice in a year. So please, this is my contact email. So if you want to contact. Thanks all.
Thank you very much, Shravan, for a very interesting presentation. Very nicely presented. Does anyone have any questions for our presenter? Okay.
Thank you, Dr. Shravan, for a very interesting presentation. My name is Mohammed Ijaz. I'm from Iran. From pioneer work from development, we know that the stability of iron carbonate steel is around 73 degrees Celsius. Is there any study to show that what sort of stability temperature? Because I'm looking at the dense phase temperature and pressure ranges at 100 bar at 40 degrees Celsius. Would iron carbonate be stable on the carbon steel surface, or would that form as a protective layer or passive enough?
Yeah, actually, so normally, normally 60 or 70 degrees centigrade, people say that FeC4-3 is more compact and can have a protection ability. So based on the limited studies, what they say is it's frequently protected at high temperature, but what exact temperature which it really gives a protective nature is unknown. And also it has an influence of a pressure which is currently unknown actually.
The second part of the question is that because most of the time, wherever you have got a carbon capture situation in the pipeline, we always have to, of course, reduce the acid gases, hydrogen sulfide, and nitrogen compounds. Is there any study in the dense phase that suggests that if you are closer to the upper water, how much hydrogen sulfide you can run on carbon steel or nitrogen?
Yeah, actually, that's an interesting question, and so it's very complex actually. If it is two systems, like for example, if you have a nitric NO2 and water, how much it is soluble we can operate. So yeah, there are some calculations which you can do to really understand what is the fraction of the liquid that goes into the common space. Yeah, there's a way that we can calculate how much.
Very practical that was wondering, because calculation-wise, thermodynamic-wise, we can actually predict. Is there any practical data and analysis has been done to get that number?
Well, actually, yeah, I haven't seen any data. I think it's more complex thing because we need to measure at the high pressure systems. So,
thank you very much.
yeah, thank you.
Thanks very much. Very interesting question. Do we have any more? Audience there? Okay.
From Iran, thank you for your presentation. So there is a big difference between the localized and the general is the rate of the tempo quoted in terms of average, or is it the actual that you see? Because if it's another case, then it's significantly more than 10 times. And I assume that it's operating at high pressure, so that would be quite sensitive failure. And the second question would be, knowing this, is there an art to control that, we want general condition?
Yeah, actually, yeah, that's a good question actually. So localized corrosion is more important. And second thing is why it is 1 order of magnitude normally higher than the general corrosion rates, because it's not the actual area that is taken into account while calculating. So that's why the general corrosions are significantly lower. Yeah, almost. So it's always important to check the localized corrosion rates. Sorry, what's your second question?
Yeah, it's, I think, you know, if that's the case, you know, we can live with the general corrosion. And so it's the art then trying to make sure that we control the corrosion in such a way that it's generally not broken.
So actually, it's a general corrosion. So the localized corrosion here, it means here is not related to the corrosion resistant alloy stainless steel. So that is different here. So the localized corrosion itself is a general corrosion, but the thing is here, the condensation happened at a particular location where the corrosion is completely much deeper than the rest of the locations where condensation happened later. So, and they consider it as a localized corrosion region. So normally we better to call it a general, but we observe it very locally there. But yeah, there's one more question as well, like why it happened very locally. So it should be, so the condensation happens, it should happen throughout the surface. It should not be at very particular location of the specimen. So again, there could be any issues with the test procedure here.
Thank you very much. One more question from Shravan Kairy.
Simon Hurst from Mencheck. It's not really a question, I think it's just more of a statement or a consideration. Hydrogen and CO2, they're both heavily prevalent on reusing existing pipelines. I think it's, excuse me, I think it's fair to say from your talk and the previous talk that there seems to be a huge number of unknowns as to how suitable those pipelines are for reuse, and actually the proof of reusing an individual pipeline could be significant, you know, in terms of the cost of actually demonstrating that you're fit to use that pipeline. I mean, Professor Cheng was talking about a finite element model, but I wasn't sure how much of a pipeline he was talking about modeling. But I mean, if you were talking about having to model, let's say, every sort of micro defect in a pipeline, you'd probably still be doing it by the time we've moved on to something else. It's my fault.
Yeah, actually, the thing is, so it depends on the concentration of the impurity. So what's the study revealed? What the studies revealed is even the corrosion resistant stainless steels have a similar corrosion rate to API grade steels, and even the highly corrosion resistant polycast alloy also experience corrosion. So because of the aggressivity of the corrosive medium forms, so normally depending on the gases impurities, the pH can be significantly lower. So so the key is controlling the concentration. So if you think that the impurities are reasonably okay, and if you can replace pipeline steels with corrosion resistant alloys, maybe need to think of, yeah. So the key is the concentration. So even more, yeah.
Yeah, I'll just add to that. So I guess it's the job of the research to identify the methods that are available, and it's the job of the operators to identify what's considered so hard in order to manage these risks going forward. That's why events like these are really important, so that we can all collaborate together to come to a consensus. But I don't think the answer is there yet. But I think with the group we have going forward, we can come up with it together to make sure that we can reuse these things in a safe manner going forward. Okay, do we have any questions online?
No.
Okay, I have one more question for yourself. So your presentation doesn't mention flow loops, and they're a really good way of kind of replicating what happens in industry, especially with existing pipeline. What are your thoughts on them and utilizing them in your research?
So yeah, that's a question actually. Even we have like, is it really need to have exact replication? So the flow loop can give you the influence of the flow rates. So yeah, so right now the question is expecting from the industry guys whether we need a really replication or right now it is important to focus on the concentration of the impurities. So yeah, any suggestions from the floor rates?
Okay, perfect. And if there's no more, I have one more question to you. So your research is based on standardization of a test method. So in an ideal pipeline, getting it from work into something that's recognized in industry, what would be the timeline or what would be the ideal process in making that happen?
Oh yeah, the standardization takes a lot of time. So literally, I do not have an experience in making a standard test methodology, but based on my the core researchers, what's the timeline is typically goes into 5 years to 8 years down the line. So it's a long process actually.
I think there's a lot of work to be done. So if anyone can help in supporting getting these methods standardized, will help everyone, and that'll be a benefit. So with that in place, I'd like our audience to thank you in the usual manner. Thank you very much.
Thanks. Thank you.
So that concludes our pipeline session. A lot of both very interesting presentations. I hope you got a lot of value out of them. So I've noticed no one has asked the most important question, is what's happening with lunch. So I believe that should be coming through shortly. We're going to be having an hour's break, so after you feel free to mingle and engage with everyone. Only a request I'll have is if you haven't signed in yet, there's a sign-in form at the front desk. You can just put your name on there to make sure you're accountable for. And feel free to mingle and cohort. Our speakers will be over here, but they'll be coming across the table and feel free to engage with us and hopefully get the most out of the networking experience. So thank you all very much, and I'll catch you all at 1 o'clock. Thank you.